Welcome back, everyone. We are now on 12.3, Shifting Equilibria, Le Chatelier's Principle. So here we're going to describe the ways in which an equilibrium system can be stressed and predict the response of a stressed equilibrium using Le Chatelier's principle. So what Le Chatelier's principle is when a chemical system is at equilibrium that is disturbed, it returns to equilibrium by counteracting this disturbance. So remember, at equilibrium, our Q is equal to K, but when we're causing a disturbance, something is happening to change Q. So our reaction is going to shift one way or the other to reestablish Q being equal to K. So for instance, let's say we add some reactant or product. The reaction is going to proceed in the direction that consumes part of what we added. If we disturb it by removing reactant or product, it's going to proceed in the direction that's going to restore what was removed. So it's going again to respond in a way that restores equilibrium and gets our Q and K equal to each other again. So let's say we add some reactant to the forward reaction, okay? So that means our forward reaction is going to increase, meaning we're going to shift our equilibrium towards the products or to the right. So we may say shifts right, shifts left. That's what we're talking about, products versus reactant side. If we remove some product or we add reactant, either one of these is going to cause our Q to be less than K, meaning our equilibrium is going to shift right. Okay, and this also holds true for changing the pressures because pressure is proportional to molar concentration. So same thing when it comes to pressure and and its effect on Q. To shift the equilibrium to the left, we can either add product, which is going to cause the reverse reaction rate to increase, shifting that reaction left. Or we can also remove reactant. So removing reactant or adding product is going to cause your QC to be greater than your K, making our equilibrium shift left. And again, since pressure is proportional to molar concentration, this holds true for changing our pressures also. Now, when it comes to changing volume for a gas phase equilibrium, it's actually a pretty interesting process because all the species in our gas phase equilibrium are occupying the same volume, right? They're all in the same space, so they have the same overall volume. So changing the volume of our system is going to have the same change in concentration for both reactants and products. But it can still shift our equilibrium. So you have to use stoichiometry to figure out how the volume change is going to affect the shift. So for example, the reaction of hydrogen and iodine gas making hydrogen iodide, we can say, QP is equal to the partial pressure of HI squared over partial pressure of hydrogen times that of I2. And let's say, and that's equal to Kp. Now let's go ahead and say that we're going to decrease our volume by a factor of 3. And what this does is it's going to increase our pressure by 3. And just to kind of prove that, PV equals nRT, right? So our pressure is equal to 1 over volume times nRT. So if we increase our volume by a factor of 3, or decrease our volume, so when we decrease volume, we're increasing pressure because they are inversely proportional to each other. So if we decrease volume, pressure goes up. So that means if we decrease the volume by 3, we're increasing the pressure by 3. So now our pressures, we have 3 times the partial pressure of HI squared over 3P for H2 times 3 times the pressure of iodine. So 3 squared is now 9 times the partial pressure of HI over total. We can multiply the 2 3's together, and that's 9 times the pressure of hydrogen times the pressure of iodine. Those 9's cancel out. So overall, there's no change here. But that doesn't hold true for everything. For instance, okay, so decreasing this volume by a factor of 3 for the hydrogen and iodine reaction had no change. But if, let's say, we do this for 2NO2 going to 2NO plus O2. So we have our QP is pressure of NO squared times O2 over NO squared. So now we have 3 times the partial pressure of NO squared times 3 times the partial pressure of O2 over 3 times the pressure of NO squared. So 3 squared is 9 times the 3 from PO2 is 20. And then, oh, actually, we don't even need to do times 3. Divided by this 3 squared is 9. So these two 9s cancel out. But we still have this 3 is still there. So now we have 3 times QP, and that is greater than KP. So since Q is greater than P, our equilibrium is shifting left. Nope. Hold on. Equilibrium is shifting left. Okay, yeah. So decreasing that volume by 3 shifts our equilibrium left. But if we were to increase our volume, it would shift it right. So you have to use stoichiometry and put in those increases to see how it's going to affect your equilibrium. Now, just like before, adding or removing a pure liquid or solid has no effect on the system unless all of it's removed, but we're not going to worry about that. And again, this is because they don't appear in the equilibrium expression. Remember, they're pure, they're equal to 1. An example of equilibrium is good old soft drinks, or sodas. So you've got that carbon dioxide dissolved in water, and it reacts to produce hydrogen carbonate, which then is ionized to give us bicarbonate and hydrogen ions. So you have 3 equilibriums going on at the same time. So we use high pressure in the systems to get the carbon dioxide to dissolve, so to get it aqueous first, and it gives us these high concentrations of dissolved carbon dioxide, and then the products from the other reactions. You fill up your bottle or can almost to the top, but you leave some headspace. And then that headspace, that space is going to actually help when it comes to the pressure of the carbon dioxide. The pressure of the CO2 in the headspace is really low, but while we get more equilibrium happening, it's shifting left, so the carbon dioxide is going more into the gaseous phase from the aqueous phase. And then that's increasing that pressure of the headspace. So when you open your can or your bottle, you hear that good old tss sound, and that's because your pressurized CO2 is escaping from your headspace, shifting your dissolution equilibrium to the left. So now that aqueous CO2 is going back into the gas phase. So gas phase on the left, aqueous on the right for CO2. And then over time, the equilibrium is overall pretty slow, which is why you can leave a soda, leave it open for like an hour, and it's still nice and bubbly because you still have CO2 dissolved in it. But if you leave it out for, a day or so, it's flat, and that actually means that you've reached equilibrium between the gaseous and aqueous carbon dioxide. And I'm weird. I actually kind of like the taste of flat soda. I don't like my soda too terribly carbonated. It gives me hiccups, and I don't know. I'm weird, I know. So changing the temperature of your system is going to actually change your equilibrium and your equilibrium constant. So remember, equilibrium constants are set for a given temperature, but if you change the temperature of your system, you're going to have a new K. So let's say we're increasing the temperature, we're increasing the heat, and our equilibrium is going to respond in a way that consumes that added heat. And again, we're changing the value of the equilibrium constant. So let's say we have an exothermic reaction. Some A plus B is in equilibrium to C plus D. And it's exothermic, meaning heat is a product. If we were to increase the temperature, that means we're increasing the heat. So that means we're going to shift our reaction to the left because we've increased a product. So now we're going to shift so we're making more of those reactants. We have more reactants. So that means that in our K expression, the denominator is getting bigger, meaning our K is getting smaller. If we have an endothermic reaction, that means heat is a reactant. So if we increase the heat here, now we're going to shift our equilibrium to the right towards the products. meaning that those two, the products now are going to be higher in concentration. So our numerator and our K expression is going to be higher. So our K is going to increase. The next thing to think about is catalysts and how they do or do not affect equilibrium. Spoiler, they don't affect equilibrium. So if you remember, a catalyst speeds up the rate of a reaction. If you have a reversible reaction, the catalyst increases the rate of the forward and reverse reactions. And the result is it causes the system to just reach equilibrium quicker. But it does not affect the equilibrium concentrations or the value of the equilibrium constant. And if you remember from we were talking about catalysis in the last chapter, in chapter 12, the catalyst is regenerated. It's not part of the rate equation. Okay, it's just there. It cancels out, so that makes sense that then it's not going to be part of our big K equilibrium constant. So here's a nice picture kind of just showing you a catalyst and what it does. Remember, it lowers the activation energy for a reaction, but it doesn't affect the value of the equilibrium constant. One example of where this is used is the Haber-Bosch process, and this is used to make industrial ammonia. Your book talks about all the different processes in it, but I'm not really worrying about it. It's just a nice example of using a catalyst to make NH3. They also use high pressures, and they continuously remove ammonia from the system. So they're doing all these different things to help shift that equilibrium to make the ammonia. And yeah, then they also use a catalyst too. If you are a chem major, you'll study this a lot more in depth in advanced inorganic chemistry.